All right, so today we're going to talk about 13.2, derivatives and integrals of vector functions. Really, this should be a relatively short section, so we'll see if we can get this done in one video. If not, it'll probably be two short videos. Um, in either case, this one should actually be relatively simple. Um, the idea itself is actually pretty simple, and it should hopefully make sense. When we're taking a derivative given a vector, so here's our vector, some function of t, g of t, h of t, um, then r prime of t, or the derivative of this, is literally just going to be the derivative of each piece. It's f prime of t, g prime of t, h prime of t. So in our first example, the calculus here is really simple. If I want to find r prime of t, again, it's going to be the derivative of each piece. The derivative of cosine of t, of course, is negative sine t. The derivative of sine of t is cosine t. And then the derivative of t is 1. So again, very simple, not really difficult to do. There's r prime of t. And, it doesn't ask this, but we're going to use this for a little bit later. Let's say we wanted to find r prime at 0. Well, then we're just going to plug 0 in for all these t's. So sine of 0 is 0, cosine of 0 is 1, and then nothing to plug in here, so that's 1. Now the real question is, what does this mean? What's actually going on here? So let's, because the second part of the question says sketch the graph of the original and the derivative and discuss its meaning. So if we draw, whoops, didn't mean to do that. Okay, let's try that again. If we draw, here's a three-dimensional plane here. All right, so we should know from what we did before that this cosine t, sine t, t is going to be a helix. It's going to be a helix which revolves around the z-axis. And again, if we start at 0, the cosine is 1, sine is 0, so x is 1, y is 0, and z is 0. So we're going to start out here. And then if we move to pi halves up here, we would get 0, 1, pi halves. So it's going to start rotating in this direction. So let me go ahead and pick a different color for that. Let's make our helix red. And it looks like it's going to do something like this. And so on. All right, so we have our directions. Actually, I'm not going to put the arrows on here, and I'm not going to put them on here for a reason, because when we go to sketch the derivative, I want to make sure that we can see what's going on with that. So what you should notice here is the derivative itself is a vector, right? R prime of t, this is a vector. It's a vector valued function. And then if I picked a specific point, 0 for t, not point, but a specific value of t, 0, and plugged it in, it gives me a vector. So we actually get a vector. What we get is a little tangent vector. That's actually what's actually happening here. So not only will we do r prime of 0, let's just pick another one so we can kind of see a couple. Let's go back to black real quick here. Let's do r prime at pi halves, just to see what's going on there. So cosine of pi halves, of course, is um, I'm sorry, not cosine, because I'm doing r prime. Negative sine of pi halves. Sine of pi halves is 1, so that's negative 1. Cosine of pi halves is 0, and then 1. So let's go ahead and take a look at what this looks like now graphically. So at 0, so when t is 0, we have the vector 0, 1, 1. But remember, this is going to come from here. It's a tangent vector off of here. So 0, 1, 1 means I'm going to go 0 in the x direction, 1 in the y direction, so out this way, 1 in the z direction, up this way. So really what it's doing is it's kind of creating, that's not very good, try that again. It's kind of creating a little tangent line to the graph, something like that. So it's, if you can kind of picture the fact that this is up It moved out this way and then up that way. So it's actually created that little right triangle there, but the tangent vector itself is kind of staying alongside of the curve as we go around the curve. And then if I were to pick another point, like I said, we picked pi halves, which is over here, but the tangent vector that's here would kind of move along the curve. The tangent vector that's here would move along the curve in this direction. So you would expect that the tangent vector that starts right here, again, let's go back to green for that. The tangent vector that starts right here should stay along the curve in this general direction. Well, let's see if that's the case. Well, at pi halves, it was -1, that is 1 in this direction in the x direction, 0 in the y direction, which makes sense, and then 1 in the z direction because we are going up a little bit, so it is going to stay tangent to that curve, kind of in that fashion right there. So what's really happening here is we are basically creating, or r prime of t, creates many tangent vectors. Creates many tangent vectors. And that's exactly what's happening. When you take the derivative, the derivative itself is a vector, and it's creating many tangent vectors to your curve. Just like when we took a derivative in two-dimensional space, it was the um, tangent slope of the curve. This is the same idea. It's the tangent vector to the curve. All right. So, just like we did in AB and BC, we can find the equation of a tangent line at a specific point. So if we do that, we need the same information as what we did before. That doesn't change. Remember in ABBC, to write the equation of a tangent line, you always needed the x, the y, or the point, and then you needed the slope. Well, we still need the slope, but the slope now is a parallel vector. Remember, that's how we get the slope of a linear equation in 3 dimensions. So what we need is a point, because this is how you write the equation of a line, right? You have to have a point and a parallel vector. There we go. So you need a point and a parallel vector. Well, we can get a point. We're specifically talking about when t is 0. I'm just going to plug 0 in for r, and that's going to be my value. That's my point. And basically, we'll call this our starting point. So if t is 0, I'm going to plug that in and get 0, 0, cosine of 0 is 1. So there is, oops, yeah, that's not the right notation because it's not a vector. R of 0. Well, I mean, it is, but it also gives us a point on the plane. The vector gets to that point, but we specifically need the point on the plane. So we're actually going to make this, there we go. We're actually going to make it a point because that's our point that we need. Yes, the vector 0, 0, 1 is also created from this. It takes us out to that point, but this is the point on the curve that we need. Then, of course, we need r prime of t. R prime of t, taking the derivative of each piece, 2t, 1, derivative of cosine is negative sine t. And then I would need specifically r prime at t. Now that is our tangent vector at that point. So plugging in 0, I get 0, 1, 0. And that's plugging that in for r prime. Oops, that was supposed to be r prime of 0. Let's try that again. There we go. So now we have our parallel vector and we have our starting point. Now we're going to write the equation of our line. We're going to write this in parametric form. Again, you could write it in parametric or you could write it in vector form. Probably don't really want to mess with symmetric form in this case. So in parametric form, x is going to be our starting point 0 plus, in this case, no change in t. So it's just 0 always. y is going to start at 0, and I do have a change in the y direction of 1, so that's going to be 0 plus 1t, or just t. And then z starts at 1 and does not have any change, so it's always 1. So there is the parametric equation for your line that is tangent to whatever this curve here looks like at the time when t equals 0. Again, not really difficult to do. Actually, I think it's somewhat easier in this case than it was in ABBC. All right, so now let's talk about this thing which is called the unit tangent vector. And we define the unit tangent vector with this capital T. So we actually call the unit tangent vector capital T of t. So that is the unit tangent vector. And this will definitely have more use after this section. So unit tangent vector. Let's break this down a little bit. Unit, meaning the magnitude is 1. And tangent vector, which is r prime of t. We just found the tangent vector above, r prime of t with a magnitude of 1. That's the unit tangent vector. So if I want to find the unit tangent vector, so t of t, well, it's a tangent vector with a magnitude of 1. Well, how do we get something to have a magnitude of 1 or be a unit vector of some kind? We take the vector and we divide it by its magnitude. So it's r prime of t divided by the magnitude of r prime of t. This is the definition for a unit tangent vector. So it's basically just a tangent vector divided by its magnitude. That will always give you a length of 1. So in this case, if I want to find the unit tangent vector, I need r prime of t and I need r prime of t's magnitude. So let's find r prime of t in this case. R prime of t. So a couple of different derivative techniques now going on here. This one's just a straight power rule. That'll be 1/2 t to the negative 1/2. The second piece is an exponential. Um, Hopefully you guys remember the pattern for an exponential derivative. In this case it's e, so it makes it even easier. This is just going to be 3 e to the 3t. And then this last one looks like we're going to have to do a quotient rule here. So let's see, the derivative of the top is 5 times the bottom minus the derivative of the bottom, which is 1 times the top, all over the bottom squared. All right, so we can clean that up just a little bit. Let's see here. That's going to be this square root t to the negative 1/2 is a square root that drops to the bottom. So that's 1 over 2 root t. Okay, 3e to the 3t. Not much we can do with that. This one here, let's see, we're going to get a 5t when we distribute here minus that 5t. That's going to go away. So I'll have a 5 left on top over t plus 1 squared. That's probably the most cleaned up version that we're going to be able to get. Then we need to take and find the magnitude of this. That's going to be fun. All right, so we need the magnitude of r prime of t. Well, remember the magnitude is squaring each one of these pieces, summing them, and then taking the square root. So the magnitude of this thing is going to be, let's see, we need a kind of a big square root here, I think. So I'm going to square this, which is going to be 1 over 4t, looks like. Squaring this is going to be 9e to the 3t squared, or e to the 6t. So that's 9, oops, that should not be, that should be plus. 9e to the 6t. And then squaring this, looks like we're going to get 25 over t plus 1 now to the fourth power. All right, so our unit tangent vector is going to be 1 over this thing times this, or excuse me, times this piece, or you could divide each piece here by this square root, which is going to be a mess. So it'd probably be better to write it as 1 over that entire square root out front here, and then times this vector right here. That would be your unit tangent vector. But it specifically asks us in this problem to find the unit tangent vector at 1, so I'm not going to worry about writing the general unit tangent vector here. I'm going to plug in 1 so we can see what we get numerically, because otherwise it's going to be a mess. So if I want to find the unit tangent vector at 1, I'm just going to plug 1 in for all these t values here. So let's see what I'm going to get for my coefficient out front. That's going to be 1 over 4. I'm just going to write this out. This will be 1 over the square root of 1/4 plus, plugging a 1 in here, that's going to give us 9e. And this is going to give us 25 over 1 plus 1 is 2 to the fourth power. 2 to the fourth power is 16. So 25 over 16. And whatever that comes out to be. And then times, plugging a 1 in here, it's going to give me a half. Plugging a 1 in here is going to give me 3e cubed. And then plugging a 1 in here is going to give me 5 over 2 squared, or 4, so 5/4. So this is my unit tangent vector at 1. All right. Again, really shouldn't be anything too extremely challenging there. We have to remember some of our derivative techniques to be able to do this stuff. But other than that, and we're not going to try and simplify something like that, especially with the e in there. It's not going to work out nicely, so we just leave it like that, and that's fine. If we were asked for a decimal approximation, then we would plug it into a calculator, but we're not in this case. All right, so let's move on. All right, so this time, it's giving us that r of 0 equals 2, 0, 1, so it looks like that is a specific vector at a specific time. And it tells us that r prime is 2t secant squared t 1 over t plus 1. They want us to find r of t. So they've given us a derivative, and then they want us to go backwards, which of course means now we're going to have to take antiderivatives or integrate. So the general idea is, just like it is with derivatives, if I want to take the integral of r of t, whatever that is, yes, I do know we have r prime of t here, but in general, if we're just going to take an antiderivative or integral of something like this, it is simply going to be the integral of f of t dt, the integral of g of t dt, and the integral of h of t dt. Now, one of the biggest things here is that we don't have any kind of bounds, and because we don't have bounds, when we do this, we are going to have to include a constant of integration, but each one of these pieces is going to have a constant of integration, which very well could be different. So we have to include a constant with each individual piece as we go through. So again, they've given us, and we'll change to this, they've given us that r of t is going to be the integral, in this case, of r prime of t dt. Because they gave us r prime, we want to find r. So we're going to go ahead and integrate. And again, we're going to integrate each individual piece of this vector. So the antiderivative of 2t is going to be t squared. But remember, it does have a constant, so we'll call this constant c1, because whatever this constant is very well might be different from all the other constants. Antiderivative of secant squared, hopefully you guys remember, is tangent of t. and then plus some other constant we'll call C2. And then the last one, 1 over t plus 1. Again, hopefully you guys remember this is a linear denominator with a constant on top, so it's going to be a natural log of the absolute value of t plus 1, and then plus some other constant C3. Okay, this can actually be written in this form, but I want to make sure I touch on something right here. This can be written as t squared tangent of t natural log absolute value of t plus 1 plus some big C. The biggest thing here is that you have to understand that big C right there is not just a single number. Like before, the C was just a value, it was just a number. In this case, C represents the vector constant of integration. Vector constant of integration. So this is a vector. It's going to have three components. It's going to have C1, C2, and C3 in this case that makes it up. So it's not just one number. It's not the same number added to all these three different pieces. It is a different, or could be a different value for C1, C2, and C3. So it's our job now to find these values. We want to find C1, C2, and C3. Well, in order to do that in Calculus ABBC, we needed an initial condition of some kind to find those constants. Well, they gave it to us. They gave it to us right here. That's our initial condition. So that we know when the t value is 0, this is what I get out for x, too. When t is 0, I get out 0 for y. When t is 0, I get out 1 for z. So we should now be able to find the c values. So in this case, when t is 0, I would get 0 squared plus c1, and that's got to equal 2. Well, of course, that just means that c1 is 2. In this case, when t is 0, so I'm going to have tangent of 0 plus c2 has to equal 0. Well, tangent of 0 is 0, so in this case, c2 is 0. And then in the last one, if I plug in 0 for t here, this one works out really nicely. I get the natural log of 0 plus 1, which of course is the natural log of 1, plus c3, and that has to equal 1. Well, natural log of 1 is 0, so c3, of course, then just equals 1. They aren't all that easy, but in this case it was pretty easy. So my r of t, specific to when r of 0 equals this gave me my initial condition. So r of t is now going to be written as t squared, and then my constant was 2 for that part. Constant for this one is 0, so it's just tangent t. And then natural log, absolute value t plus 1, and then my constant was 1. So this, whoops, is our r of t. Whoops, lost my vector notation. There we go. So that is our r of t, specific to when r of 0 was 2, 0, 1. All right, one more concept. We are actually going to talk about this concept of smooth. We are not doing any of these because I'm not in class, and this is a short day for you guys anyway, so this is a great lesson for this day. All right, so we're going to talk about this concept of smooth. And yeah, we can put it right here. We got plenty of room. So smooth. Come on. Smooth. Not like this thing is writing. This is not writing smooth. All right. A curve to write slow, it looks like here, is said to be smooth wow, if r prime of t is defined everywhere and r prime of t does not equal the zero vector for any value of t. So a curve is said to be smooth if r prime is defined everywhere, so we don't have any undefined values of r prime anywhere, and r prime of t cannot be made the zero vector for any value of t. So if I can plug some value of t into my r prime and I get 0, 0, 0, it is not considered a smooth curve. And hopefully that makes some sense. That this r prime, remember this is the tangent vector. If I get a tangent vector that has no vector to it, then it's not really a tangent vector. There's no tangent vector there. So in this case, it would have to be something where the derivative basically doesn't exist. And if you think about what we did in calculus ABBC, we had a couple of places specifically that the derivative didn't exist, but it was still a continuous curve, and that was something where it made a corner or a cusp. Something like that would be something where the derivative wouldn't exist, even though the point did exist there. And it's the same general idea um, on this. So let's take a look at, let's create one. We'll call r of t, so this is our space curve, um, t squared, t to the fourth, t to the sixth. There. So we want to figure out if this is a smooth curve. Well, if we take r prime of t, it must exist everywhere. So r prime of t is 2t, 4t cubed, and 6t to the fifth. Okay, this is definitely defined everywhere. There's no problem putting any value of t in there, right? Defined everywhere. Or basically for every value of t. However, it should be very obvious in this case, and that's why I picked this one. If I let t equal 0, so r prime of 0, then we would get 0, 0, 0. We would get a 0 vector right there. So this is not a smooth curve because of that. So let's take a look at kind of what this looks like. I'll try and do my best here to sketch this for you. So if we take and just kind of sketch a very general three-dimensional plane here. The curve itself, um, r of t, so if we let r of t start at, well, I guess it would technically start if we start at 0, it's 0, 0, 0. So let's go in red here for that. So we would have a point that starts there. As t gets larger, so if t is 1, we're at 1, 1, 1, which is 1, 1, 1 right here. And then if we plug in 2, the number is going to start getting big fast. It's going to be 4, 16, what is that, 64? 4, 16, 64. This thing starts to get big very, very, very quickly. So it's actually going to go kind of weird because the z direction is going to kind of go off like this. It's actually going to shape like this, I believe. Maybe I have it backwards, but it doesn't matter. Either way, it's going to have the same general idea. Um, if I was in class here, I'd pull up the calc plot to show you guys. But if I go in the negative direction, aren't I going to get basically the same thing? The only difference is um, my t values are going to be negative now, so it's actually going to look like this. Something like that, I believe. In any case, what you have right there is the cusp. And you can see that at 0 you would have um, no tangent vector. So it's not a smooth curve. It's going to bend down, it's going to cusp, and then it's going to go back out. So this is not a smooth curve. But ultimately, algebraically, this is what we're looking for. R prime of t has to be defined everywhere, and R of t, or excuse me, R prime of t cannot be made the 0 vector for any value of t. That's the big concept right there. All right, you guys should have plenty enough. That's good enough for today.